There are literally tens of thousands of complex products or systems out there in the marketplace, from smartphones to electric cars to military jet fighters and everything in between. What each of these products has in common is the fact that, like people, they have what's called a life cycle. The life cycle from a human perspective, or the human species overall's perspective, starts out with the definition of our genetic code, or the template that dictates that we're human rather than, say, an apple or a leopard or a leaf. This template is replicated millions of times and results in you and me and everyone that's around us. We live our own individual lives within the confines of all of human existence for that template. We might only be around for about 80 years or so individually, but our species will hopefully be around for quite some time. The point is, everything has a life cycle, from complex people to complex products or systems. And this course is about those processes that we use to bring complex products and systems into existence and live out their own individual life cycles, both as a template or design and as individual systems that are owned and operated by regular people like you and me. This method is called systems engineering, and it's gaining widespread use because it's been found to be the most efficient way to bring complex products into existence at acceptable levels of quality and risk. Systems engineering is an approach to bringing complex products into existence from the top down, meaning that we take a problem or a need for our product and we define the characteristics about it at very high, abstract levels, and then we split those characteristics up into smaller chunks and characterize each of those chunks in greater detail. And we keep going with this, decomposing characteristics and elements about our product into smaller and smaller segments until a team of engineers and managers can handle bringing them into existence, something that we call implementation. And then these implemented segments are attached together, something that we call integration, and we test them out to see if they work the way we want them to, something that we call verification and validation, or just testing. And once we have a design we're happy with, we can start producing them in production factories and sending them out into the marketplace for you and I to purchase and use until we use them up and eventually dispose of them. As I just described, systems engineering is a method for us to manage bringing something complex into existence, something that users will gain value out of, that's worth their time and money to own and operate. Also, something that's worth it for your organization to develop. A return on investment, in other words. Successful systems are developed using a win-win strategy, where one would expect the customer and the supplier are better off and happier after the transaction. This means we need a way to manage the development of our system, control the risks, and keep us from fielding a failed product. And this product, it's high quality and it's reliable. This is the essence of systems engineering. There are many introduction to systems engineering and product development courses out there on public sites or offered through universities. And from my own research, either they're incredibly short, lasting only a couple of hours, to lasting for what seems like too long, stretch across the entire academic semester, for instance. Many of the longer courses out there are too detailed for what your organization might be looking for. Perhaps you don't need to learn a very specific niche, but want to focus on the broader aspects of product development and systems engineering. Alternatively, the shorter introductory courses and certification boot camps are simply too short, focusing on memorizing processes and terminology rather than the big picture and how it all really fits together. That's fine if your team members are already intimately familiar with systems engineering and have been doing it for a long time. Many systems engineering courses are also not offered online, so your team members have to travel out to take the courses and require accommodations and time away from the office for this. Also, many systems engineering courses speak to tailored or specific systems engineering processes and standards within their own enterprise. For instance, the Department of Defense has its own processes and terminology. The interesting thing here, and what you'll learn in this course, is that tailored processes and terminology really boil down to the same things in the end. It's just called by different names. If I'm bold enough to say, which I apparently am, all of product development and systems engineering really boils down to using the very same scientific method that you learned about in grade school, but we're applying it to really complex systems that are just too difficult to manage alone or even with a small team. This course was designed to fit that gap in the learning market, where the length of the course is hopefully just long enough to get your team up and running to hone their skills to better develop your product line. This course, since it's offered online, doesn't require travel and accommodations, and it also aligns with ISO, IEC, IEEE Standard 15288, and the Incose standard. So if you're taking this for the Incose certification, you should be able to pass the certification exam after you've watched these videos. There are a few other Incose certification boot camps that are much shorter than this course, but like I said, they often focus on the processes and terminology and don't really go too deep into how it all really fits together and into a cohesive, big picture in terms of product development and life cycle of the system. And that's why this course was developed. So, who is this course for? Based on the discussion so far, it's primarily aimed at teams that want to bring complex products into existence and have them perform as the users would like or expect. It's also aimed at grad school students that are getting masters in engineering field or business field and would benefit from this course. If your capstone project or thesis has to do with bringing a complex system into existence, then this course would be valuable to you. Research labs that focus on advancing technologies and bring new innovative solutions into the marketplace could also benefit from this course. Startup companies that are seeking to develop and field their inventions, assuming an invention you have is of a complex product or system that's too difficult to manage with just a small team of people, then you would benefit from this course. In the same light, if your organization is a large firm that specializes in developing or improving already existing complex systems, then this course would benefit you as well. Examples of these kind of organizations would be jetliner manufacturers. If you are part of an organization like this, then this course would provide you a perfect primer for developing or improving your products, training team members, understanding industry standards, and what the developer's role is in the life cycle of the products that you're developing. If you're a part of a government organization that defines and oversees system development, then this course would also benefit you. You would gain the training for systems engineering and product development, understand system development from industry standards, and understand the role government agencies play in the life cycle of products that they want to develop. You could have come across this course if you're already a systems engineer and are seeking certification with the International Council on Systems Engineering, or Incose. This course will provide you with more than enough information to take and pass the Incose certification exam. This course aligns with both the Incose Systems Engineering Handbook and ISO IEC IEEE Standard 15288, which captures the international standards for systems engineering and product development worldwide. The benefits you gain from taking this course include reducing the risk of overspending your budget for your product development effort or exceeding the schedule that you've laid out. It will also teach you how to plan and organize your product's organization and layout by architecting the structure of your system from the top down, identifying and defining your system's requirements, its interactions with the outside world, its internal functions, and its widgets or components. This course will help you learn how far down into your system you need to define and capture, deep enough that software programmers or component engineers can then take over, implementing those lower-level components within your system. This course will give you what you need in order to estimate the scope of your development efforts in terms of cost, schedule, and technical complexity or risk. It will also help you identify other elements most people don't think about when they develop complex systems, like the infrastructure that's required that enables you to define and develop the system in the first place. Last but not least, this course will help you define and develop, implement, integrate, test, produce, and deploy and sustain your product successfully, where you, the developer, as well as the user, will be purchasing or using your system, and will be satisfied and accomplish the goals that we all set out to accomplish by using that system. The course will teach you about increasing reliability of your system, improving quality, and reducing overall risk from cost, schedule, and technical performance perspectives. The topics for this course are arranged in overarching categories, which align with the Incose Systems Engineering Handbook, as well as the ISO IEC IEEE Standard 15288. Throughout this course, I'll be using a few different systems as examples. I'll be using aircraft, cars, and the automated teller machine, where the ATM is the most used example throughout this course. I use the ATM as the primary example system in this course because the ATM is a machine that we're all familiar with, and most of us have used it, and it's a machine whose behaviors we can wrap our heads around. Cars and aircraft are a bit more complex and may likely lead to confusion unless the student's already familiar with the inner workings of cars and airplanes, so I usually choose to use the simpler ATM as the primary system throughout this course. Anyway, the first set of lessons will define systems, systems engineering, its benefits, the system's contexts and boundaries, and the overarching systems engineering activities like constructing and refining these requirements, behavioral, mission, physical domains, will then advance into the brief introduction of the lifecycle stages that most systems undergo as they're brought from idea into reality. The second set of lessons will walk through each of the lifecycle technical processes, beginning at the beginning with your idea, and ending with the end of the system's life during the disposal process. Intermixed throughout the lifecycle processes, I'll be introducing topics relevant to those processes, like writing requirements, creating functions and functional flows, writing use cases, planning for tests, and constructing the physical characteristics of your system. The third set of lessons dives into the processes that you would use across the entire life cycle of the system's creation. It doesn't matter where you are and how mature the design is. Topics include risk management, configuration management, project planning and project management, requirements management and specifications, information and measurement management, decision management, also called trade studies, and quality management, basically anything with the word management at the end. In fact, these are formally called the technical management processes. The fourth set of lessons are a short but impactful explanation of what's called the agreement processes. And this is where you have a buyer and a seller and the contractual relationship between them. Earlier I mentioned you'll learn what the developer's role is in the product lifecycle and what the government's role is. It's here that you'll learn those roles. The lessons here are for what's called the acquisition process and the supply process, the buyer and the seller's own individual processes. The fifth set of lessons dives into the processes that allow you, from a holistic perspective, to manage your development efforts. These are called enterprise processes or project enabling processes. They include topics like cycle management, infrastructure management, portfolio and human resource management, as well as portfolio and knowledge management. The sixth set of lessons familiarize you with how to tailor any of these processes to suit your personal organization's needs and the various tools and techniques that you can use to bring your ideas into reality more efficiently with less risk. Topics here include lifecycle tailoring, modeling and simulation, object-oriented systems engineering and software development, prototyping, integrated product development, mean systems engineering, agile systems engineering, system of systems, and enterprise systems. As a systems engineer or project manager, you'll be required to give direction and guidance to your development team throughout your product's lifecycle. To be effective at making the right decisions or better decisions, you need to know a little bit about what everyone does in your team, what their specialty areas are. So the seventh set of lessons has to do with familiarizing you with these subject matter areas. These areas include affordability and value engineering, electromagnetic compatibility, environmental engineering, reliability, system safety, human system integration or human-machine interfacing, system security, product support, and resilience. This captures all the topics that will be covered in this course, over 100 lessons in total, averaging about 15 minutes each. This is enough to get you and your team started with developing a product right away, and that's my goal for this course. I'll finish this introduction video with introducing myself. My name is Christopher Olson. I started out with product development and systems engineering all the way back in the mid-1990s when I was a system user in the U.S. Army in the Air Cavalry. After my military service, I was in civil aviation for a few years, working with mostly helicopters and some airplanes, until I found my way into the acquisition environment for the U.S. Navy. There I performed project management and systems engineering responsibilities for over a decade. Some of the programs I supported include the H-1 Attack and Utility Helicopter Program, the Presidential Helicopter Program, heavy lift helicopters, the CH-53 Kilo, the FA-18 Hornet jet fighters, the F-35 Lightning stealth jet fighter, and the E-2D Hawkeye surveillance aircraft programs. During my experience, I worked with major system developers, including Bell Helicopter Textron, Boeing, Lockheed Martin, Augusta and Westland European Helicopters, Sikorsky Helicopters, Raytheon, Northrop Grumman, and Honeywell, just to name a few. During that time, I also started teaching systems engineering and then creating systems engineering courses with Johns Hopkins University. I earned my Bachelor of Science from Embry-Riddle Aeronautical University and my Master's in Systems Engineering from Johns Hopkins University. I'm currently an adjunct professor and course manager for a course I created at Johns Hopkins, a course which won Best Online Course at the Whiting School of Engineering and where I received the Best Online Instructor Award. The Johns Hopkins Systems Engineering Program is the first ABET certified systems engineering program, leading the way for the other systems engineering programs throughout the country, and it's ranked in the top 3 best online engineering programs nationally, at least according to the U.S. News and World Report. I'm also a graduate student mentor, having helped over 100 students graduate with honors from the systems engineering program at Johns Hopkins. For certifications, I'm certified through the U.S. Department of Defense, something they call DAWIA, which stands for Defense Acquisition Workforce Improvement Act. I have 2 separate DAWIA certifications, one in systems engineering and the other in program management. Both are at the highest level, which is level 3. I'm also Incose CCEP certified and a member of Incose. I also have a Program Management Professional, or PMP, certification from the Program Management Institute, or PMI. Finally, I'll also mention I have a system modeling certification called the OCSMP, or Object Management Group Certified System Modeling Professional, which you'll come to learn has to do with system modeling and architecting using the system modeling language called SysML for short. With that, I hope you get a lot out of this course. Go ahead and get started with Lesson 1. Everything we will be learning throughout this course and through our product development efforts hinges on the concept of the system. So let's get this most critical subject out of the way first. There's no better place to begin learning about this subject than by defining what we mean when we use the word system. Okay, so a system, as defined by the International Standards of Organization, or ISO for short, is that systems are a combination of interacting elements organized to achieve one or more stated purposes. Recall that a system is a combination of interacting elements organized to achieve one or more stated purposes. The first term is to define is interacting, and this term is going to come up a lot throughout this course and your experiences as a product developer. To put simply, interacting implies a collection or a group of parts that exist within a system that work together. Think of a set of gears intermeshed, where one gear turns the others. Moving on, for those that learn through repetition, the definition of a system is that it's a combination of interacting elements organized to achieve one or more stated purposes. The next term we have is a set of elements. These are essentially piece parts that make up the system. These can be products, like pieces of hardware and software. System elements can also be composed or processes used to make the system operate or maintain its operation. A system element can include people that will be interacting with the system or that have a vested interest in the system, people that we call stakeholders. System elements can include information used by the system or generated by the system. Think about the various sensors spread throughout your car, providing information to the brains of the vehicle, which allow it to do things like economize the fuel or adjust braking forces or internal temperatures. System elements can include techniques used to operate and maintain the system, or in other words, specific ways the system can be used or how the system goes about performing its tasks or missions. These techniques are not limited to the system only when it's in operation. They can also include design techniques or production techniques, and so on. System elements also include facilities. When we think of facilities, we often jump to some sort of storage or housing facility to protect the system from the elements when it's not in use. An aircraft hangar, for example, is a facility. But it's not the only kind of facility. A system facility can also include facilities used in its development or when it's being tested, for example, using a wind tunnel or firing range. Facilities can include production facilities, or maintenance facilities, or even temporary storage facilities. These facilities are considered a part of our system elements. As you can tell, there's a lot more to a system than just the actual system itself. One of the most important things to consider is that the system provides services. Its internal elements also provide internal services for each other, or perhaps something outside of the system, like the user. Services play a critical role in product development. So this subject of services is going to come up a lot throughout this course. Speaking of services, that's in fact what the last part of our definition pertains to. For the purposes of helping you remember the definition of a system, in case you have to take a test or something, it's a combination of interacting elements organized to achieve one or more stated purposes. The stated purposes is just as the name implies. It's an agreed-to purpose or primary goal of the system. It's the purpose for which the system exists. The stated purpose for a passenger car is to safely and reliably transport passengers and its driver and passengers to specific distances. A stated purpose for a jet fighter could be to safely and reliably surveil, detect, identify, and attrite and assess enemy targets. A stated purpose for a front-end loader could be to safely and reliably move X amount of earth over Y amount of time. Before we continue, let's pause here and read over these additional definitions of a system from other sources. IEEE is considered an international authority on the subject of both general engineering and systems engineering. Notice that each of these definitions is telling relatively the same story, that a system is some entity, usually human-made, that was created to execute some mission for a user that has a desired goal in mind, through a specific operational environment. A computer that you can buy off the shelf at a store is a perfect example of a system. Why is it a system? As you can see, there's a lot of elements that make up a desktop computer. These elements are all integrated, interacting with each other to accomplish the defined objectives for the computer. Some of these defined objectives are to accept incoming data, process that data, and provide some useful information as an output. This particular depiction shows the composition of the computer, or in other words, it shows what the computer is composed of. This composition relationship forms the foundation for the concept of system hierarchies, which is the topic of the next lesson. There are several definitions of a system out there, but they're all relatively the same, only stated in different ways. For this course, we'll be using the ISO definition, which is that a system is a combination of interacting elements organized to achieve one or more stated purposes. As a systems engineer, you'll find it valuable and useful to decompose a system into smaller, more manageable pieces. We do this by creating what's called a system hierarchy of our system. To begin this lesson about system hierarchies, let's define what it is academically. A system hierarchy, according to the International Standards Organization, it's an organizational representation of a system structure using partitioning relationships. Partitioning is displayed as a set of elements within a system, focusing on the relationships of those elements to the next higher order element, while not focusing on the details for how those elements interact or interface with each other. Here, we're merely focused on what the system elements are composed of. In our unique systems engineering language, we define each layer of a system's hierarchy a particular way. In general, here's how they're decomposed. At the top is this system itself. In this example, the car is the system. If we were to decompose the car from that point and show all of the next level elements, the next layer down is what we might call the subsystem layer. These subsystems are a collection of system elements that, when they are integrated, they fulfill the primary goals of the overall car system, like the engine subsystem on this car, working with the transmission and the chassis and the wheels and the brakes and the electric power subsystem, all to accomplish its higher order goal of providing transportation services to the user. When a series of subsystems work together, then the system as a whole should be performing its primary missions. The next layer below the subsystem are the components, and these work together when they are integrated to perform the operations of a subsystem. Examples of components for the engine subsystem might include the piston assemblies, the fuel injection system, exhaust, engine accessories, and drive, the engine spark, and so on. We can keep decomposing our system to lower and lower levels, achieving greater levels of detail, getting more specific as we progress downward. In the next level down, components are comprised of various subcomponents, and these elements operate together in an integrated fashion once again to allow each component to perform its primary functions. At the bottom of our hierarchy are typically what are called parts. These are individual items that, when they are combined together, they make up the subcomponents. I'm not going to show them here, but examples can include the piston rings or the nuts and the bolts and the screws that hold things together, like mounting brackets and so on. Most of the time, you'll see a systems hierarchy expressed using words to describe system elements rather than graphics or pictures like what you just saw. We've got the primary element, the system, at the top, and it gets decomposed into lower tier elements as you progress downward. Now keep in mind that defining the system and its lower tiered elements entirely in context and how your organization needs to categorize them. Here's an example of a SysML block definition diagram. In SysML, or the System Modeling Language, and UML, the Unified Modeling Language, we show composite associations as a little black diamond at the higher order end. When you see a composite association, think of the words "is comprised of" as you read from the top to the bottom, or if you're reading from the bottom to the top, think of the words "is a part of" as you go upward. In other words, the system is composed of subsystems. Each subsystem is composed of various components. Each component is composed of subcomponents, and each subcomponent is composed of various parts. Or alternatively, if we go from the bottom up, each part is a part of a subcomponent, and each subcomponent is a part of a component, and so on. This layout assumes that all the components and the parts and so on are all different configurations from each other. So what if a subcomponent is composed of more than one part of the same configuration? For example, we may have 4 bolts holding on a bracket. These bolts are all the same configuration. Or what if we have 4 tires that are exactly the same on our car? They're all made of the same material, they have the same part number, and so on. We don't have to show each and every tire or each and every bolt in our hierarchy. Instead, we can show what's called a multiplicity. And this is shown at the very bottom of our chart for part 2.2.2.4. And here we're saying that there are 4 of these parts, whatever they happen to be, that help compose subcomponent 2.2.2. Here's a block definition diagram for our vehicle from earlier in this lesson. And there's a few things to point out in this diagram. Notice how the composition relationships are showing that the car system is composed of 9 different subsystems. It's the powertrain, the power, starting and charging, suspension and handling, and so on. This is shown by the little black diamond at the parent or the higher order level. Notice how the power subsystem is decomposed also. The power subsystem, it's composed of multiple components as well. Some of the components are the engine block, air metering, the engine head, the cooling, and so on. To illustrate the usage of multiplicities, I've decomposed the power generation component into subcomponents. The power generation component is composed of 4 pistons, 4 piston rods, and 4 piston rod pins. This is shown in the multiplicities next to the composition line. To further bring the point home, notice that the piston is composed of a single piston head and 3 piston rings. System hierarchies are dependent on the context that they're used for. For example, if we are an auto manufacturer in our organization, our vehicles might be at the top of our hierarchies, while the engine, the transmission, suspension, and so on are all one level below the subsystem levels in our context. Alternatively, if we're an engine manufacturer and not a car manufacturer, then we care most about our engine because this is our primary product. Therefore, in the engine manufacturer's context, the engine is going to be at the top of their hierarchy, while the internal components to the engine are at the next layer down, elements like the pistons and the crankshaft and the spark plugs and so on. Here's a view of the power subsystem, or the engine subsystem, if you want to call it that. As I just mentioned, the power subsystem is considered the system level in this configuration or in this context. Something that's worth mentioning in this particular diagram is the use of the parts compartment below the piston block. Instead of showing that the piston head and the piston rings in the hierarchical format, we can use the parts compartment instead. This is handy when we want to show decomposition through a single path for an entire system hierarchy. Also, notice the multiplicities is included next to the parts as well. One final note before we leave this diagram. In the system modeling language, the usage of the word part is a little bit different than the system hierarchy language in general. When we talk about a systems hierarchy, parts are usually the lowest level elements, like I just said a few slides ago. These are individual nuts and bolts and gaskets and so on. However, in the system modeling language, this isn't the case. In the system modeling language, a quote part is just an element that's only one level lower in the hierarchy than the currently looked at or selected element. So the engine block, the power generation, air metering, engine timing, and so on are all considered quote parts from the perspective of the power subsystem. And the same like the piston rod pins, and the pistons are considered parts from the perspective of the power generation component. Just keep that in mind as we proceed. In addition, hierarchies are also specific to various domains. You'll learn about domains in a separate lesson, but for now, think about the hierarchies we have shown here are in the physical domain. That is, we're displaying physical pieces of hardware and software. It's simpler to understand for our purposes of teaching hierarchies since they're tangible elements that we can see and touch and we have experiences with. Representing abstract domains in hierarchies might lead to confusion, at least for an introductory student, so we have to save that for further lessons. The physical hierarchies that I just showed you were not displaying system behaviors or an organizational chart, for example. It's also possible to show the behaviors of a system in a hierarchical format, as well as the chain of command within your organization, for instance. In these domains, we could create a system behavior hierarchy, where the overall system is decomposed into lower order behaviors that together help accomplish the higher order behavior. This is something known as functional decomposition, which is a subject that you'll learn a lot more about in future lessons. One question that's often asked is, how far should you decompose your product or your system hierarchy? So, should you break down every single element within your system all the way down to the nuts and bolts, or is it good enough to break it down a few layers? No, the answer to this depends on the purpose of the hierarchy. When engineering a system, hierarchies are typically a product of conceptual development, capturing the concept in the form of abstract boxes and symbols rather than actual pieces of hardware and software, because we haven't gotten to that point yet. So we're just trying to capture and organize our system into a coherent fashion that allows us to manage its future development. That is what systems engineering is all about, after all. It's about managing complexity. Therefore, in this context, you want to decompose the hierarchy down to a level where the individual element in question can be developed and integrated with the other elements with either a small team or one person, perhaps, to a manageable level, in other words. This typically means that it would be decomposed down to the component or subcomponent level for most systems, while the design engineers will figure out what the smaller piece parts will be inside of each of these elements. Other criteria for the depth of decomposition is that if it can be determined that the element in question can be created or engineered in-house, or if it can be purchased by another organization that can build it for us, or if it can be reused from another system, then further decomposition is usually not required. This is a concept known as a make or buy decision. One final note about hierarchies before we get to the next lesson. It should be stated that hierarchies are a product of developing a system and not created first and then followed up by the design of the system. The hierarchy is a representation of the results of engineering or constructing a system for each element within the system. The hierarchy is used to communicate the construction of the system and to allow us to compartmentalize or partition the various complex elements that we've created. This allows us to form design teams that can specialize in the development of each particular system element to go off and develop each of these separate domains.